Timeless Concepts from Physics Helpline. In this video tutorial, we will discuss the periodicity of trigonometric ratios, which will lead us to an useful method for the determination of the values of any trigonometric ratio of any large angle. Let us recall that angles are traced with reference to the positive direction of the x-axis. The radius vector OA starting from OX has traced angle AOB is equal to theta to reach the position OA as shown in the first figure, where B is the foot of the perpendicular dropped from A upon x-axis. Therefore, from definition we have sin theta is equal to AB by OA, cos theta is equal to OB by OA, and tan theta is equal to AB by OB. Now let us consider the second figure. In this case, the radius vector has traced an angle theta and then from this position has further traced n anti-clock rotations. Therefore, the total angle traced is equal to theta plus 2n pi, since one rotation is equal to 2 pi radians. We note that the radius vector has come back to position OA as shown. Therefore, the values of the trigonometric ratios will be the same as those for angle theta. Similarly, it can be seen that if the radius vector, after tracing a positive angle theta, further traced n clockwise rotations, then the total angle traced is equal to theta minus 2n pi, as the angle traced is negative for clockwise rotations. In this case also, the radius vector would come back to OA, giving us the same values of the trigonometric functions as shown in the third figure. Therefore, we conclude that by adding or subtracting an integral multiple of 2 pi radians to an angle theta, the value of the trigonometric function remains unchanged. Using these concepts, we can find the value of any trigonometric function of any large angle. As an illustration, we will find the value of sine 3000 degrees. In the first step, we express the angle 3000 degrees as 2n pi plus theta. For this, we divide 3000 by 360, which gives a quotient 8 and a remainder 120. Therefore, we have sine 3000 is equal to sine of 8 into 360 plus 120. In the second step, we subtract 8 into 360 from the angle, which, according to the concepts discussed, will not change the value of the function in any way. This gives sine 3000 degrees is equal to sine 120 degrees. In the third step, we find the value of sine 120. Now, sine 120 is equal to sine 90 plus 30, which is equal to cos 30, since sine 90 plus theta is equal to cos theta. Therefore, we get sine 3000 degrees is equal to cos 30, which is equal to plus root 3 by 2, which is the required answer. Now we will discuss an alternate method which is more convenient for the following reason. In the first method, we divide the given angle by 360, which will produce a remainder lying between 0 and 360, corresponding to any of the four quadrants. Therefore, sometimes finding the value of the trigonometric function becomes tedious. Hence, let us understand a simpler and more convenient method. For this, let us first understand the values of angles at the quadrant boundaries x, y, x dash and y dash as the radius vector arrives there after successive rotations. We start with angle 0 when the radius vector is at x initially. When it reaches y, the value of the angle is equal to pi by 2. Similarly, the values of the angle at x dash and y dash are 2 pi by 2 and 3 pi by 2. Finally, it arrives back at x where the angle is 4 pi by 2. We note that the angle at x has increased by 4 pi by 2 after one rotation. Therefore, after subsequent rotations, the angles at x will be 8 pi by 2, 12 pi by 2, etc. Therefore, we generally represent the angle at x as 4n pi by 2, where n is equal to 0, 1, 2, etc. Similarly, at y, the initial angle is equal to pi by 2. After the first rotation, it becomes 5 pi by 2, and after the subsequent rotations, the angles will be 9 pi by 2, 13 pi by 2, etc. Therefore, we generally represent the angle at y as 4n plus 1 into pi by 2, where n is equal to 0, 1, 2, etc. Similarly, one can easily see that the angles at x dash and y dash may be generally represented as 4n plus 2 into pi by 2 and 4n plus 3 into pi by 2 respectively, where n is equal to 0, 1, 2, etc. We note that at x and x dash we get even multiples of pi by 2, and at y and y dash we get odd multiples of pi by 2. Now let us note the values of trigonometric ratios for the angles 90 minus theta, 90 plus theta, 180 minus theta, 180 plus theta, 270 minus theta, 270 plus theta, and 360 minus theta. These angles, along with the quadrants and the values of sine and cos, are listed in the table. From the table, it is clear that for angles 90 plus or minus theta and 270 plus or minus theta, That is, for the odd multiples of pi by 2, we get the complementary function, and for 180 plus or minus theta and 360 plus or minus theta, that is, for even multiples of pi by 2, we get the same function. Now, let us understand the formula to be used, which is written as sin n pi by 2 plus theta is equal to plus or minus sin theta when n is even, and it is equal to plus or minus cos theta when n is odd. This formula, even though written for sine, it is applicable to other trigonometric functions as well. Whether the value is positive or negative can be determined by considering the given function and the quadrant in which the given angle lies. Now we will find the value of sine 3000 degrees using this formula. In the first step, we will express the angle 3000 degrees as n pi by 2 plus theta. For this, we divide 3000 by 90, which gives a quotient 33 and a remainder 30. Therefore, we write sine 3000 is equal to sine 33 into 90 plus 30, which is equal to plus or minus cos 30, since n is equal to 33 is odd. In the second step, we determine whether it is positive or negative. We note that 33 pi by 2 comes at y. Therefore, 3000 degrees lies in the second quadrant. Also, the given function is sine, which is positive in the second quadrant. Therefore, we get sine 3000 degrees is equal to plus cos 30, which is equal to plus root 3 by 2, which is the same as the answer obtained in the previous method. This completes the theory of the periodicity of trigonometric ratios.